Hello everyone and welcome back. Let's continue on with the chapter of dynamics for AS level physics. AS level physics. Now, so far, we have not only gone through all of the Newton's laws of motion, but more importantly, what we had discussed in our previous lesson was the idea of momentum. So let's do a quick recap first before we go any further. So we had discussed and in fact defined momentum as the product of mass and velocity. From there, we were able to link momentum and resultant force through the definition of the resultant force, wherein we had described the resultant force as the rate of change of momentum. And from there, you may remember, we were able to use Newton's second law of motion to figure out a formula that could relate resultant force in terms of momentum, and we were able to get change in momentum over a time duration or a time interval, right? Now, this was quite an important feat because now we've basically introduced a new physical quantity, one that we call momentum. Now we want to explore some properties regarding momentum beyond it just being a vector quantity. That even if you remember, we had even mentioned that too. So let me write that over here. Now we want to go beyond this, and to do that, we can actually explore one kind of interaction that I had already mentioned before. You might remember those as collisions. The reason why collisions are so important for us is because collisions are the kind of interaction that's the best example for you to actually see how a force between two colliding objects can cause things like momentum to change. So let us explore this concept further, and you'll realize that we're going to slowly inch towards a very important conservation law. So important that it's in fact just as important as the law of conservation of energy. So let's approach that phenomenon. So let's cut off our revision here and proceed. We'll in fact proceed with the case of two billiard balls. Suppose you have this green ball with a mass m1 and a red ball, or let's make it purple, with a mass m2. So two billiard balls, and they're moving with some initial velocity, u1 for the green ball and u2 for the purple ball. Now we wish to see how when these two balls collide, we want to see basically what happens to the momentum of each of these objects, and is there a situation where the momenta before and after collision are somehow linked with each other. So suppose before collision you have the scenario that I've already drawn here, before collision, and then after collision suppose the balls still have the same mass, of course, just as we expect, but this time suppose they have some new values of velocity. Suppose the green ball has a velocity v1 and the purple ball has a velocity v2. Now, because we're looking at and we're interested in studying the collision specifically, we want to enclose these two billiard balls in this closed container such that it doesn't get disturbed from the outside world, right? So basically what we mean to say is that because I'm so interested in studying collisions, I want to make sure that there aren't any external forces that could possibly disturb my system. So how could I fix that? Well, all I need to do is enclose my two billiard balls in a container. So imagine me drawing these walls around the two billiard balls that I wish to study. And then imagine that I'm sending this off to deep space. So what in effect I'm doing is that I'm closing my two billiard balls off of the environment. So there's this closed notion to it. I'll in fact write it here. And I have isolated these two billiard balls such that there are no external influences that could possibly affect it. So what I've in effect created is an environment that is closed, and more importantly, it's isolated. So from here on out, the kind of system we'll be treating is definitely going to be something that's closed and isolated. So let me recall and rewrite their notions. Closed here specifically means that we're basically drawing a boundary between the system and the surrounding. and it's a rigid boundary, so we don't expect it to change or somehow become, allow some kind of external influence to come in. So it's drawing a rigid boundary around the system, our system being the 2 billiard balls. And when the system is isolated, what we mean to say is that no external influences or no external forces, let's say, can influence our system, right? So now that we've got this out of the way, now with this kind of a situation, we can be sure, like 100% sure, that any collisions that will occur between the objects, we can ensure that they're not going to be disturbed by any external influence, right? Now let's actually explore the notion of this collision. And for this, let's actually look at the situation of the 2 billiard balls during a collision. So before they had their initial velocities u1, u2, and after collision they have new velocities v1 and v2. So we wish to explore what happens when they're during their own collision. So during collision, at least visually speaking, you can expect the system will look something like this. You have m1 colliding very close and is in contact with the purple ball. Now, during this collision, we know that a force is definitely going to be exerted, right? And there will be a force that the green ball exerts on the purple ball. Let's call that force F1. So I repeat, F1 is the force exerted by ball 1 on ball 2. Now this kind of a description might be ringing some alarm bells in your mind, right? You might remember that this kind of a description of forces we would expect in Newton's third law as well. Where in Newton's third law, you might remember, we discussed that when there's an action force, there has to be a reaction force. So in this situation, what do you think the reaction force will be? Give it a thought. Well, did you guess it? In this case, the action force is F1, which is the force that the green ball exerts on the purple ball. And in turn, the reaction force will be the force that the purple ball, ball 2, exerts on ball 1. So it's going to be directed in the opposite direction, like so. That's F2. So it's the force exerted by ball 2 on ball 1. And if we bring back the notion of Newton's third law, according to Newton's third law, we remember that the action and reaction pair of forces were equal in magnitude and had to be directed in opposite directions. So them being equal in magnitude simply means F1 is equal to F2, and if they have to be directed in opposite directions, that means one of these should have a negative sign to represent that opposite direction. So I've placed it here, right? Now we can explore this even further, because just in our previous lesson, we managed to express force in terms of a change in momentum, remember? In fact, we revised it right over here. So let me rewrite forces F1 and F2 in terms of the changes in momentum per unit time. Now F1, since it's the force that the green ball is exerting, or ball number 1 is exerting, I can rewrite F1 as the rate of change of momentum specifically for ball 1 whereas for F2 I can write it as the rate of change of momentum, but this time for ball 2. So let me rewrite this in a more equation-like format. For F1 I can write it as change in momentum for ball 1 divided by the time interval of collision, and for F2 I can write it as the change in momentum for ball 2 divided by the time interval. Now notice how I don't give any subscripts 1 and 2 to these time intervals, because if you think about it, both balls are sharing the same collision, right? So they're going to collide with each other with the same time duration. So we'll have the same time duration of collision. Now if we expect this, we can basically expect the same time duration on both sides, in which case it's just a matter of multiplying by delta t on both sides to cancel these out. And in the end, we get a change in momentum for ball 1 equals negative the change in momentum for ball 2. Since we know the old before collision velocities and after collision velocities, we can actually rewrite these changes in momentum. So just to kind of recap what was happening before collision and after collision. Before collision, we had this scenario where ball 1 had initial velocity u1 and ball 2 had initial velocity u2. And then after collision, you had the same masses m1 and m2, but this time we suppose they have new final velocities v1 and v2. Right? Now we can express the changes in velocity for each of them one by one. Let's first do it for ball 1, which would just be these green balls that I've highlighted in yellow. That change in momentum would just be the final momentum of ball 1 minus the initial momentum of ball 1. Whereas for the ball number 2, which I've highlighted in orange over here, it's going to be the same thing. But this time there will be a negative sign. So negative final momentum of the second ball minus the initial momentum of the second ball. Now it's just a matter of plugging in the numbers. So the final momentum of ball 1 is m1 times v1. And the initial momentum of ball number 1 specifically is m1 u1. Notice how I give them positive signs only because they're directed in the same direction. And so we have m1 u1. Now same thing goes for the ball number 2. Final momentum is m2 v2 and initial momentum is m2 u2. Now it's just a matter of me expanding this bracket. m1 v1 minus m1 u1 equals minus m2 v2 plus m2 u2. Now I can make things simpler by shifting all of the initial velocities to one side and all the final velocities to the other side, in which case I get m1 v1 plus m2 v2 equals m1 u1 plus m2 u2. Now if you look at your system back again, which I've drawn up above, you can see how m1 v1 plus m2 v2, you can basically break it down further. m1 v1 is the final momentum. When I say final, I mean momentum after collision. So it's the final momentum of ball 1. m2 v2 is the final momentum of ball 2. And m1 u1 is the initial momentum of ball 1 and m2 u2 is the initial momentum of ball 2. So what you've concluded is something quite remarkable. What you have concluded through this result is that the total momentum after collision, that's basically what PF, the momentum for the final momentum for ball 1 plus final momentum for ball 2 is. That's the total momentum after collision. That just so happens to be equal to the total momentum before collision. Now this might not seem quite remarkable, but seeing how it's occurring from Newton's laws of motion gives us quite a deep insight into how momentum, specifically total momenta, can be for a closed isolated system. What we've managed to show is that for a closed isolated system, the individual momenta before and after collision can definitely change. We can see that based on the fact that the values of velocities are changing for each of the individual balls. However, they must change in such a way that the total momentum does not change. Total momentum does not change. This is you basically saying that the total momentum stays conserved. And this is precisely what we wanted to achieve in the end. I repeat, what we've concluded is that total momentum stays conserved because it's a quantity that's staying constant for a closed isolated system. This, what I've written right here and I'm highlighting in yellow, is basically the essence of what we call the principle of conservation of momentum. So at this stage, it's very important for us to basically summarize all that we have written so far in a more complete manner. So I repeat, what we'll write right now is the principle of conservation of momentum. And we can describe it as follows. It states that for a closed isolated system, the total momentum stays conserved. Or you could say that the total momentum stays constant. And when you claim such a thing, what you're claiming is that the total momentum before collision, must be equal to the total momentum after collision. Now it's really this result that's the crux of dealing with closed isolated systems and using this to figure out what the new velocities or initial velocities are before and after some kind of a collision. However, this would only hold if you have a closed isolated system, right? Now, sometimes students are inclined to just memorize this formula, the one I'm highlighting right now, and then just apply it every time. But do remember that this final form might not be the case every time. It ultimately depends on how the two balls or any two objects for that matter, it really matters on how they're colliding with each other. So this formula we got when we were talking about this system where you had balls 1 and 2 moving in the same direction before collision as well as after collision. Let's look at a scenario where you have the system still moving before collision and after collision, like they're still colliding with each other, the two billiard balls that is. However, suppose you have the two billiard balls approaching each other and then moving away from each other after collision. So it would look something like this. You have ball M1 moving with initial velocity U1 and ball M2 moving with initial velocity U2, but this time in the opposite direction. So in this scenario before collision, I'll even write it here, before collision, you have the billiard balls approaching each other. And let's suppose after collision, they move away from each other. So let's suppose you had M1 and M2, but this time they move away. So the purple ball is now moving towards the right with a new velocity, while ball 1 or the green ball is moving towards the left with a new velocity V1. So now let's see how we can use the principle of conservation of momentum to figure out what the final expression will be that relates each of these momenta. Now, like we just mentioned, the principle still holds that the total momentum before collision must be equal to the total momentum after collision. It always helps to solve each of these individually, so let's do that first. Now, when I talk about the total momentum before collision, it's just the momentum of ball 1 plus the momentum of ball 2. So momentum is just mass times velocity, right? But keeping in mind direction. So the green ball would have a momentum of m1u1 plus, now the purple ball would have a momentum of m2u2 with a negative sign. Why? Because it's moving in the opposite direction. So here, the expression we get for total momentum before collision is m1u1 minus m2u2. Let's see what do we get for the scenario of total momentum after collision. In fact, I want you to give this a try just for pause this video and give it a try. Now let's see what do we get. It'll be the same, of course, momentum of ball 1 plus momentum of ball 2. But this time for ball 1, you have a new velocity v that not only has a new magnitude of v1, but also has the opposite direction. So this time the momentum of ball 1 will be minus m1 v1 plus, and for the second ball, it's just m2 v2. So now we have the total momentum after collision. And since we just mentioned, the principle of conservation of momentum will hold no matter what, we can equate the two in the end to get m1 u1 minus m2u2 equals minus m1v1 plus m2v2. And so this becomes our final result. Now this equation, oftentimes you will be asked to construct such an equation before you can even solve some unknown value. The way they can present that unknown value is something like in the following manner. So suppose it's the same scenario as before, where before collision you have the situation where you have the green ball of mass 10 kg moving with an initial velocity of, let's say, 5 meters per second, approaching another ball of mass 20 kg moving in the opposite direction with a velocity of, let's say, 1 meters per second. That's your first situation before collision. And then after collision, suppose that after collision you notice that the 10 kg ball has moved away with a new final velocity of, let's suppose, 2 meters per second. So your question is this: what is the final velocity of the second ball? Now here too, you'll basically have to relate the situations or the variables before and after collision. And the best way you can do that is by using the principle of conservation of momentum, right? That would be as so. So for the situation before collision, that would just be the momentum of the 10 kg mass plus the momentum of the 20 kg mass, right? So for the 10 kg mass, it would be 10 times 5 added with 20 times minus 1. Why? Because it's in the opposite direction, right? So here we get 50 minus 20 equals 30 kg meters per second, right? That's your total momentum before collision. Now let's construct an equation for the situation after collision, for the total momentum, that is. Now here it would be 10 times minus 2 because it's in the opposite direction, then 10 kg mass. And then for the second 20 kg mass, you don't know, you have its mass of course, but you don't know what its final velocity is. So we can leave it as an unknown v2. We can simplify things and we get minus 20 plus 20 times v2. And now it's just a matter of equating the two. And why we can do that? Because we know that the principle of conservation of momentum holds. You know that the total momentum before collision, which is 30, should equal the total momentum after collision, which is minus 20 times plus 20 times v2. Now it's just a matter of solving for this unknown. So I can add 20 on both sides. That allows me to cancel out the 20 here on the right hand side, and we get 50 equals 20 v2. Now I can divide by 20 on both sides, so that 20 cancels out on the right hand side in the numerator and the denominator, and I will get v2 equals 5 over 2, which you can always bring it to 2.5 meters per second. My bad. But the point is that you can construct your equation by first using the principle of conservation of momentum as your motivation. You'll find the total momentum before collision, find the total momentum after collision, and then in the end, it's just a matter of solving this to the point where you get the value of the unknown, right? Now, clearly we have a huge variety of collisions, right? We first started off with the situation where both balls move in the same direction before and after collision. We then explored the situation where you have the two balls approaching each other before collision and then moving away from each other. You can then imagine that there is a huge variety when it comes to the kinds of collisions you can have. So it always helps to categorize the types of collisions that we can have. And in that sense, we actually have primarily two types of collisions. One type is what we call elastic collision. And the other type is what we call inelastic collisions. Now it turns out that they're not categorized based on whether or not they obey the principle of conservation of momentum. That's not possible if you think about it, right? Because if you realize The principle of conservation of momentum is something quite universal, so you'll always expect it to work no matter what. The factor based on which these two types of collisions arise is based on whether or not they conserve kinetic energy. In that sense, we define elastic collisions as those collisions wherein the total kinetic energy stays conserved. And in this situation where we're talking about inelastic collisions, we define them as, they're basically in contrast to elastic collisions. So these are those collisions wherein the total kinetic energy does not stay conserved. Now this might seem pretty strange to claim, right? Because it's very rare for us to look at a situation where a type of energy is conserved and then in another where it's not conserved. But you have to remember, we're talking about total kinetic energy, not total energy. We know for a fact from the principle of conservation of energy that no matter what system you have, the total energy must stay constant no matter what, right? But here we're talking about a specific type of energy and whether or not it's being conserved. For elastic collisions, what we see and in fact claim is that the total kinetic energy is what's staying conserved, right? When we say it's conserved, that means specifically in context of collisions, what that means is that the total kinetic energy before collision, must be equal to the total kinetic energy after collision. This is, in a way, an ideal situation where there is no loss or gain of kinetic energy involved. But in the case of inelastic collisions, they are not going to be equal anymore. So total kinetic energy before collision will not be equal to the total kinetic energy after collision. Now, even now, you might be thinking that, okay, this is way too strange if you think about it. In what kind of a scenario can you expect the total kinetic energy before and after collision to not be the same? Well, it's quite common if you think about it, right? Think of a car that was moving with some velocity before. Let's actually make this trolley over here. It was moving with some velocity. Now, do note, I'm not necessarily drawing a collision here. In fact, we could even draw a collision. Let's actually make it specific. Suppose you have this wall over here. This ball, and let's say the wall has some mass, clearly it's not moving. And let's say you have this trolley moving forward and then colliding with the wall and then it stops. It had a non-zero velocity before, but then finally its velocity dropped to zero. Clearly you can see that before collision, there was definitely some non-zero kinetic energy for the system. My system being the trolley and the wall. But then after collision, I can see how both the trolley and the wall both are stationary. So let me illustrate this, or write it down rather. Before collision, the trolley was moving and the wall was not moving. The wall was stationary, as we expect, right? But then after collision, the trolley and wall both are stationary. So we can clearly see how in the before scenario there was kinetic energy that was non-zero for the entire system of the trolley and the wall. But then after collision, that total kinetic energy somehow just dropped to zero. So it's perfectly valid for a situation of inelastic collisions to occur, wherein the total kinetic energy before and after collisions are no longer the same. But when it comes to elastic collisions, they can be the same. Now it must be noted here, and although I've mentioned it before, it's still worth mentioning either way. Yes, you have these two types of collisions, and yes, they're differentiated based on whether or not they conserved total kinetic energy. But no matter what type of collision you have, I'll in fact write it here because it's quite important. No matter what type of collision you have, two things will never change. Or, okay, let's actually put it this way. No matter what type of collision you have, whether it's elastic or inelastic, the principle of conservation of momentum and the law of conservation of energy, these two principles will always apply no matter what. So, in other words, no matter what type of collision you're talking about, two things will always be true. Two things will always hold. Number one, total momentum will always be conserved. And secondly, total energy is always conserved. So we have to be careful in keeping these two facts in mind before we talk about both types of collisions. Right? Alright, so what have we covered so far? We were first able to introduce and recap the concept of momentum and the resultant force. Then we talked about collisions in a more general manner, where we talked about the situation where we have two billiard balls in a closed, isolated system, meaning it's in a box that has a rigid boundary around the system that separates it from the surrounding, and it's isolated in a way that there are no external forces that could disturb it. During collision, we realized that there's an action and a reaction force acting on both balls that we labeled F1 and F2. And then using the definition of the resultant force as the rate of change of momentum, we were able to break down the equation in such a way that we were able to conclude something very fundamental about closed, isolated systems. That is, the total momentum after collision will always be equal to the total momentum before collision. That is basically comprised within what we call the principle of conservation of momentum, where we state that for a closed, isolated system, the total momentum must stay constant. And then we were able to show how we can apply that principle to different scenarios. One of which we explored was the situation of two balls approaching each other before collision and then moving away from each other. We were able to solve one question numerically. And then we described two types of collisions, elastic collisions and inelastic collisions, wherein elastic collisions are those kinds of collisions where the total kinetic energy stays conserved, while for inelastic collisions, the total kinetic energy does not stay conserved. Now, admittedly, it might seem like a big jump when it comes to introducing elastic and inelastic collisions, but it must be noted that we must spend a bit more time in understanding some examples of these two types of collisions, and that's actually going to be our goal in the next two lessons that will follow. So, we'll meet then. Thank you.